In this lecture, we will discuss about electric flux due to point charge. In the previous lecture, we have discussed what is electric flux and how it can be calculated. Now, we will discuss here the behavior of point charge and assumption of a surface about this here. In this lecture, we will be able to learn what is point charge and if something is a point charge, then how many types of charge particles, what is the arrangement of charge, then how flux can be calculated using assumption of a surface, symmetric surface, and the problems. We will discuss some problems, how it can be solved. If you are having only a single charge, then it can be considered as point charge. Whereas if you are having a large number of charge particles, then these charges combine to give some different arrangements. One of them are, if you arrange the particle in a linear direction, then it can be, say, then it is in wire form, or sometimes it may have some random arrangements. So it can be dealt differently. The electric flux of a point charge, now we can calculate, and suppose you are having a point charge which is situated in a spherical cavity. We have assumed here a spherical cavity. The point charge is shown here by the red color, and we want to check the electric flux. Then we can put our electric charge in a surface that is called Gaussian surface normally, which is asymmetric most of the time. So keep your charge in this. Now we start from phi E is equal to E dot dA. As we must be aware that phi E is the flux, and this flux is equal to, normally is equal to E dot dA. But since we are considering the field may be non-uniform, then we have just assumed that for a small element dA, the flux is d phi. And now we can calculate the total flux by adding all. And for continuous, in addition is replaced by integral. So while calculating this, we have just used this integral E dot EA. It is shown here, then this is your charge, and the small area element is shown here, it is dA. And from there, if you integrate this, we can calculate electric field, flux and the electric field. The electric field is given by E is equal to 1 upon 4 pi epsilon 0 q over r square. As we know, the for spheric sphere, you have total area is 4 pi r square. So by this you can calculate the electric field. This problem has spherical symmetry. Therefore, we use a sphere as Gaussian surface. Since E is radial, its dot product with different area vector is also radial and is always 1. E is the small same as every point on the surface. In this slide, we will learn how to calculate electric flux on point charge. For these reasons, suppose E can be pulled out from the integral, and why we may take regions for pulling out. Yes, electric field is uniform. If electric field is uniform everywhere, it can be pulled out. And we have taken symmetric area, so it is taken pulled out for a point charge. So phi E can be done as E integral of dA. Now the integral over the surface area of the sphere, we know that it is A is equal to 4 pi r square. And so if you together keep everything, then phi E is equal to EA, or phi E is equal to 1 upon 4 pi epsilon 0 q over r square 4 pi r square. Yes, in place of A we have used 4 pi r square area. We have simplified this due to uniform electric field. If the field is not same everywhere, then it cannot be done, cannot be pulled out from the E. So we have calculated phi E is equal to q over epsilon 0. So basically we have calculated flux of point charge. Soon we will realize that this will also give an important result. In the next lecture we will discuss about Gauss law. It's similar to this. Actually Q is the enclosed charge. We will discuss the actual detail in next lecture. Now we will discuss one or two problems. Suppose a point charge is contained in a spherical shape. The point charge is shown here. Now suppose we shift this charge, we move this charge from here to here by some amount. Now the question is, how does the different electric flux d phi E through the surface ds, we have chosen ds in the top side, the flux through the ds changes when the charge is moved from position 1 to position 2. Before going any answer, think over it. What we are asking? We are asking for d phi E, differential electric flux. The flux is passing through ds definitely, and the flux we are talking about, I'm not talking about total flux, I'm talking about only flux at ds. Is it increases, decreases, or doesn't change? We are moving our particle towards the ds where we want to calculate. The total flux of charge is constant with the density of flux line higher the closer by you are to be the charge. The total flux is charge is constant, but the flux line being higher to the closer you are to the charge. Therefore, as you move the charger close to the surface element, the flux line increases. And due to this, multiplying this higher density by the same value for the area ds, we will see that the incremental flux increases. So this should be the answer. The flux is increases, that from as we discussed from for A and B, because it is moving towards ds. Now take another example. Same example. The charge is inside the sphere and we are moving this charge towards ds. Now the thing is whether the total flux, I am talking about total flux, whether the total flux will change or not. Increases, decreases, doesn't change. Mind this, here I'm not talking about the flux only at ds, but I'm talking about total flux from the entire surface. We have previously calculated the total flux from the point charge depends only upon the charge, doesn't depend on distance, so does not change. So these are the few basic examples to understand fluid lines. Now we are in position to define Gaussian surface. A Gaussian surface is an imaginary surface around the charge distribution arbitrarily chosen for its symmetry. So the electric field coming through the imaginary surface is fairly constant through all the surface. Basically, a Gaussian surface is a symmetric surface and closed surface. We will use this Gaussian surface concept in the next lecture also while explaining Gauss law. We will also study about many kinds of charge. Here I have discussed point charge. Point charge is a charge concentrated at one point. For this, we take spherical surface as a Gaussian surface, and which the area of this Gaussian surface is 4 pi r square. However, for wire, suppose your charge is in the form of wire, then the Gaussian surface will be a cylinder, because the condition of the Gaussian surface is it should be enclosed the charge. So this should be cylinder, and we know the cylinder area is 2 pi RH. If you can't say anything about the distribution of charge, then it is strange shape. Any shape can be obtained, and in this strange shape the area can be calculated by calculus. There is one more option for capacitor, parallel plate capacitor, where the surface area can be given by length and breadth of these plates. So these four categories are there for using Gaussian surface. We will discuss this Gaussian surface idea in the next lecture in detail. Thanks. I advise you to practice several problems using book on flux and its calculation. Thank you.